This video will be a brief explanation on how to get started with Autodesk Fusion 360 for manufacturing. So basically, we have a few steps that we have to talk about. First, we're going to discuss how to import a file by using the open menu here, the drop-down menu. And then how to manipulate the file in the software, which is cloud-based. So you have this panel and you're going to be able to use the data panel. Once we have the part already set up in the design space, we will switch to manufacture workspace, and then we're going to start making the manufacturing operations. The very first thing you need to do when you start with your Autodesk Fusion 360 is to either design your part on the software or to import a design from a previously used CAD software. If you want to do your design on Autodesk Fusion, it's just like any other CAD software. It has all the capabilities for creating a sketch, for example, creating circles, extruding squares, extruding all types of shapes. Just like any other CAD software, you also have Surface Works, Sheet Metal Works, and some tools here as well. We're not really going to be using this feature here. This is just going to be a brief demonstration on how to proceed for manufacturing with the software. So the very first thing that we're going to do is to import a file into the software. In this case, we'll be using this part right here. Our goal is to manufacture this part right here. It's just a regular arm for a motorcycle part. And the very first thing you need to do is to click on File, Open, and then you can either select it from the cloud of the software. We're going to discuss about it a little later, or you can open from your computer. In this case here, if you click on Open from your computer, you will see this menu here, and then you can select the SolidWorks or any other CAD file that you made with another software to be imported into Autodesk Fusion. I generally use SolidWorks for all my parts, so if you guys right click on any of these parts here, you're gonna see that the extension of the file is .sldprt. That stands for SolidWorks parts. I generally use SolidWorks for modeling, so I'm just gonna import my .sldprt part in my Autodesk Fusion design, and then I will start manipulating it from there. But one thing that I do have to tell you is that it's generally much faster when you're using step files, for example here. So in SolidWorks, when you click on Save As, and then you can choose the type of file, for example here, step files, it will generally go faster in processing this new file into Autodesk Fusion 360. However, if you just have a SolidWorks part like this, the Autodesk software does recognize SolidWorks files. You can see here that when I click on import, the SLDPRT part, it's actually processing it, and it's actually gonna be able to open the part straight from SolidWorks, which is really good. But sometimes if you have a very complex shape, that might not be the best idea. You may be better off if you just export the file on SolidWorks from SLDPRT into step file first, and then you import the step file into Autodesk Fusion. This might process a little faster here if you have a complex shaped part. Once we have the part in here, I didn't really use the part that I just imported, it was already here. So once you open the part, you can pretty much do anything that you would do with a step file in any other CAD software or any CAD model, any solid model. You can create new sketches, create new planes, and start constructing stuff, start extruding stuff, start filling up holes, making fillets, you name it, just like any other regular CAD software, okay? In our case, we're not really going to change anything in this file. Remember, this is just a tutorial, quick introduction on how to get started with manufacturing. So we're going to switch from the design workspace to the manufacture workspace. One thing that's very interesting from Autodesk Fusion is that whenever you pass the mouse on top of something and you let it sit there for about 2 seconds, it's gonna give you a brief explanation on what this thing exactly means, what this command exactly does. So it's a very good software for this matter, and you should definitely take your time and read through it. Whenever you see something that you're not familiar with, you're gonna be able to see what it actually does. So for example, here we have design, generative design, render. You can do rendering here, animations just like SolidWorks animations or any CAD software animation, simulation for checking stresses and stress concentration and all of that stuff, and also manufacturing. That's what we're concerned here today. We're gonna switch from the design to manufacture. Once you switch from design to manufacture, the manufacturing tools all appear here. Again, if you just let the mouse sit there, it's gonna show you exactly what each operation means. For example, 2D milling operation, we're into milling, turning, additive manufacturing, probing, fabrication, and utilities. We're gonna be using milling. This is basically a milling machine work. And we have here a few 2D operations that we can choose from. I'm not really gonna go through all of them. This is just a very brief explanation today, but you can switch between 2D and 3D. Whenever you can, try to use 2D operations. They're a little simpler. They have a simpler toolpath and might be a little faster. But if you have complex shapes, definitely look into using 3D operations. It might be the way to go, okay? We also have drilling operations and other commands here. For example, actions to simulate once you're done programming and generating your G code. So the very first thing I need to tell you guys is that it's a very good idea to always have your setup complete before you start making your manufacturing operations, okay? In other words, you guys can see that I have a vise right here and we have a table right here. It's very important for you to have these things because once you simulate your programming, you will be able to see if the tools or the head of your machine is gonna crash into something, for example, the vise or any other fixture that might be around here. So make sure you always add your fixtures in your drawing, okay? One thing that I also have to tell you is that it's this software, the commands for the mouse, you can choose to best fit your what software you are already used to. So if you click on your name on the top right here, then you click on preferences, you will be able to switch from the regular type of mouse command to the actual software that you're used to. In my case here, if you see the general panel, you see preference controlling general UI behavior. You'll be able to change the pan, zoom, and orbit shortcuts from Autodesk Fusion to SolidWorks. I'm already used to it. It's very hard to get used to a new software. It's not hard, but it can be pretty annoying. So you can switch it right here if you're already used to SolidWorks. So you switch to SolidWorks. If you need to change your units, you can also go through this panel here and change your standards. Z up, for example, or Y up. In my case, we're using our machine is that has the Z axis going up, so we're gonna keep at Z up. Then we click on OK. Also keep in mind that this here needs to be consistent with your machine, the units, so you can switch from inches to metric to millimeter right here. That's the very first thing you should be concerned when you're working with your part, okay? Now, going back to the table here, we're using a Haas mini mill with a Kurt vise. How did I get these things here? The Kurt vise, for example, the drawing for this, I got it from online. Sometimes the manufacturer of the vise will give you the 3D drawing for the fixture that you want to use. So it makes it very easy for you to add it to the assembly. Now, if you want to add it to the assembly, you have to switch from manufacturer to design and do all of your assembling in the design workspace, okay? Now, once we add the vise, how did I get to this table here? SolidWorks, Autodesk Fusion also has a very interesting capability. If you click right here on your Show Data panel, and if you click on at home, if you click on your home screen, you'll be able to scroll down and actually see samples right here. You can click on CAM samples, and then you have a few different manufacturers of CNC machines. For example, Haas demos. You can actually see the VF2 table and a fixture here, and you can also see a bunch of different types of fixtures right here. For example, a table with a vise, table with another fixture, just two vices, a chuck, and so on and so forth for turning operation as well and milling operations. So explore this might be very useful, very helpful. You can also see clamps here. So this might be very helpful if you want to create your setup here before simulating, so you can see any potential crashes. It's extremely important to have this in mind. Okay, that's it that I wanted to show you in the data panel. If you click on home, you're gonna have your home menu here again. I'm gonna hide it for now so we have a better view. And now we're gonna start doing the manufacturing operations per se. So what do you have to do when you very first start to program something for manufacturing? Again, switch your unit. If you have to use, if you have your machine in metric, in millimeters, switch it to millimeters. If it's in inches, switch it to inches. Once you're done with this, you create a new setup. So you're gonna go to milling, setup, a new setup. The very first thing you need to do, in this first window here, you have the setup window, stocking window, and post-process. We're gonna go through all of them, but the very first thing you need to do in your setup window is to select your model. Which one are we gonna be working with? And it's this one right here. So I'm not working with the vise, for example. I'm working with only this one. So I have to make sure this is selected. If you select something else by accident, for example, the table, you see two bodies here, just remove it and select the one that you're actually interested in working with, which is this one. Now, X, Y, and Z. This will be your G54 coordinate system in your CNC machine. If you're not planning to use any other coordinate system besides G54, let's say you want to use G55, 56 or something else, I suggest you to not change this. This is standard in machining. Try to always stick with G54 when you can. If you cannot, if you for some reason you need to keep the G54 for something else, then yeah, go ahead and use it. But you will have to change a few other settings here. For example, WCS, work coordinate system in the machine. You have to change this here and make sure your G code is exporting the correct G code for you instead of G54. Okay. I'm gonna put in the description of the video a few one link for standard G codes, so you know what I'm talking about. If you're new in machining, G54 is a very important code, and it actually means that it is gonna be your zero. So if you're not familiar with it, try to be a little familiarize yourself with some very common G codes. Okay, G54 is one of them. Now, once we have our body selected here, our work coordinate system, in my case here, in our case, we're gonna be putting it in the back left corner of our stock material. So if you guys notice, the blue body is the selected body that we're planning to machine out of the stock material. The stock material is the yellow, transparent, translucent square or rectangle that you actually see here. So we need to make sure that our stock material is in the back left corner of our stock material. Okay, our zero work coordinate system 0 is in the back left of our stock material. So I'm going to click on box point for stock point, and I'm going to click on the back left corner. Okay, remember the X, the Y, and the Z, they need to be consistent with your machine. In our case, we're using a Haas mini mill, and yes, we have the X positive to the right, the Y positive away from you. So if you use the right hand rule, positive X right, positive Y away from you, positive Z up. Okay, just think of your thumb. The thumb is going to be pointing up when you do your right hand rule. Okay, so this is consistent to our machine X, Y, and Z, and we have it to the point that we actually want it. Why do I want it right here? Because when I use edge finder, I'm gonna be touching my edge finder on the left edge and on the back edge right here to zero it. In my case, I'll be touching it with on the jaw of the vise to zero the Y, and on the jaw of the vise on the outside part right here where the mouse is at to zero the X. So touch the edge finder here, zero the X, touch the edge finder here, zero the Y. And then the stock material will be lined up with the back left corner of the jaw of the vise, not the back, the front left corner of the jaw of the vise, the back jaw. Okay. Stock material. It's standard from the software to leave it as relative size box. I generally try to not use relative size box here. I try to use always a fixed size box, and again, if you just pass the mouse and let it sit there for a few seconds, it will show you the difference between them. You can go through it on your own later. But basically, if you use a fixed size box, you basically tell the software what's the width, depth, and height of your stock material that you're going to be using. This is much better for me in my case because I try to use always when I can scrap aluminum, scrap steel. So I don't really know, like I don't really have a cut to the dimensions that I want to cut it yet. So I just grab the scrap material whenever I can use it. I just don't cut it, I just measure it and make sure it matches my dimensions right here. So in this case, I'm just gonna put any random numbers here just to make sure we're clear, we're big enough with the stock material, so when we cut outside here, the tool is not gonna be hitting the jaws of the vise. So in this case, I'm gonna leave about 3.7 inches on the Y direction. Let's see if this is gonna be good enough. Yeah, 3.7 should be fine here. And then on the X direction, I'm gonna probably leave it at 6 inches. And again, 0 is gonna be the back left corner of our stock material. Okay. Height for the Z. If you guys orbit this thing and then you click on the left right here on the right top corner, you'll notice that the maximum height of this part is less than half an inch, right? Or almost half an inch. We have a little bit extra on the top and on the bottom here. If you, let's say you put a quarter of an inch here, oh, sorry, not here, this is round to nearest, right here on the height. If you put a quarter of an inch here, it's gonna be red. This means that your stock material is not high enough, it's not thick enough to make the part that you actually want. So you want to make sure this is at least the thickness of your part right here. Otherwise, if your stock material is not the thickness of your part, you're just not going to have the real deal. Okay? You're not going to have what you're actually programming for. Now if we go 0.49, so it's still a little bigger, 0.48, 47. Now you notice that 0.47 is already shorter than my part. So 0.475 will be bigger. You can figure out like how big your part is by changing the number here or just measuring it straight with the inspect tool. Then you click on measure and you can measure from here. So if you select the top face and the bottom face, it will give you the maximum thickness. It's 0.472. So in this case, your stock material needs to be either half an inch or 0.472. In our case here, our stock material will be a half an inch. Why did I leave it at half inch? Because we can cut the rest from the top there. So what I'm gonna show you guys here is that we're leaving at half inch, and then we're gonna, instead of positioning the model on the center of the height, I'm gonna go offset from bottom, and instead of this number here, I'm gonna put 0. You will notice that the part is actually gonna drop down to the minimum height here. So we still have this thin layer to get rid of on the stock material. So you can actually position your part on the stock material based off the center, like if it's right on the center of the XYZ, or if it's offset from one of the sides. So it's a very useful capability here. Once we have this set up, let me go back to my 3.7 here on the Y. Oh, not too much. 3.6, 3.3, 3.2, 3.1, 3.3. Yeah, let's leave it like 3.3. This is just a demo. If I were to be doing this exactly how I will be doing, I would make sure that the stock material is actually tangent to the jaws here. I'm not going to do this right now because it's just a sample for the operations. We're not really concerned about it at this time. Okay. Once you have the stock material properly set here and your setup properly ready to go, XYZ on the top left back corner, then you can click on post process. Only change this if you really want to have a standard number for your programming, but in this case I'm just gonna leave it as is. Click on OK, and then we can start with our operations. Okay, before starting this video, I have already made some operations here. We're just gonna stick to the operations that I made. So which one did I do first? First one was cleaning the top of the part. By the way, whenever you're done doing an operation, if you just want to rename it so it's easier for you to identify them, you just click on the name and then you can rename it. Okay, this name is going to be the same name as it appears in the G code in a comment format of the G code. So it's always a good idea to name these things here so you know what you're actually doing or not on your part. This is for showing or not showing the operations if you just remove the mouse here. But I'm not really gonna show this. It's a little inconvenient to see when you're showing everything. It's only gonna show when you pass the mouse on the operation. Okay. If you drop this menu here, it's gonna be showing you the tool that you're using, basically the slides that this operation will be in a G code format. Okay. Now, what type of operation are we using here? It's a 2D. In this case, we're using a 2D or no, a 3D adaptive cleaning. Why am I using a 3D adaptive cleaning? If you guys notice the shape of this part here, it's not perfectly flat. If you can see this here, there is a little ramp here. When you have complex shapes like this, it might be a good idea to just use a 3D contour or a 3D cleaning. Okay, this will help you a little bit in generating the G code or generating the toolpath for your part. So how did I do this? How did I create this one here? Basically, you click on 3D adaptive cleaning, and the very first thing that you have to do is to set up a tool. You have a few windows here, or tabs. We're gonna go tab by tab, but the first one is tool, geometry, heights, passes, and linking. Let's go to the tool one first. Very first thing you need to do is to select your tool. How do you select this? You can either import libraries, or if you work in a place that they already have these things set up for you, you can ask them for the setup or the libraries. But if you want to start from scratch, you can create a tool right here. Once you open up the select tool window, click on new milling tool or new mill tool, and then you can go to the first tab, general, give your description, vendor, product ID, product link if you want to. This helps you to keep track of things. Then you can click on the cutter, and then you can select a ball end mill, a flat end mill, bull nose end mill, you name it, drill bit, center drill bit for different types of operations. In our case, we're going to be using a flat end mill, 2 flutes, carbide, no through tool coolant in inches. Okay, these details I'm gonna discuss them in a future video, but this is not a subject for the current video. Properties of carbide tools, high-speed steel tools, or lengths, diameters of tools, number of flutes. These are details that we're going to be discussing later. We're not worried about it at this moment. But basically here, make sure you always match as much as you can, as accurate as you can, your tool here. Because let's say you put a different length than your tool is actually has here. If you just run the simulation, it might work, but when you do it in real life, you may crash the machine because your tool is not long enough to cut the entire part. So always try to match here as accurate as possible to the reality, to the real world that you're actually using, okay? Once you're done setting up the cutter, you can set up the holder. Shaft, I'm not really concerned about it at this moment, but the holder, for example, always try to match something very similar to what you actually use. If it's a Cat 40, Cat 30, you name it, try to find it here. If it's not the exact one, at least something similar, okay? And if you can't find something similar, try to look it up online, try to import it from somewhere online. Once you're done with the holder, feeds and speeds. When you set up the feed and speed here, this will be the standard feeds and speeds for the tool in whichever other operation that you start using this tool. So it's a good idea to have some standard numbers here, because when you start another operation, you don't have to set it up all over again in your setup, in your tool setup tab there in your operation. So it's all gonna be ready to go there. Post processor. Again, going back to feeds and speeds, I'm not really going to talk about this because this is very specific. There are calculators online how to calculate these things. I'm going to go through it later in a later video, but for now, as of now, we're going to use standard numbers that I have already figured it out, okay? In the post-process tab, this is very important here, that the number of your tool that you're programming right now matches the number that you have set up this tool in the machine. In other words, if you're using a 1/4 of an inch end mill on position number 3 of your machine, let's say you have a carousel that holds up to 10 tools. The carousel tool number 3 needs to match this number here. If you're using a 1/4 of an inch diameter end mill in your programming for NC number 3, that means whenever it starts this operation, it's gonna call tool number 3 on your machine. So therefore, you have to have your tool number 3 in your machine as a 1/4 inch end mill. So they need to be consistent. They need to be the same, okay? Make sure this matches here. Once you're done, I'm not gonna save this because I already have it saved. You're gonna see your tool right here, and then you click on select. You can click on select tool and click on OK. And then that operation specifically is gonna be made with the tool that you just selected. In this case, I'm using the tool number 2, a 1/4 of an inch flat end mill. Second one here, coolant. Are you using coolant or not? Are you using an air system or not? You can choose it right here. I'm gonna be flooding coolant, so it's gonna activate. If I'm not mistaken, it's the M8 code. It's code is for starting the coolant and not non-stop, okay? Coolant flood. So that's M8 right here. Feeds and speeds, we're not gonna go through these here as of now, but keep in mind right here, plunge feed rate. This is extremely critical. If you go too fast when you're plunging a tool here, you may crash your machine, you may crash your tool. So this is very critical to be not too low, but low enough so that the tool doesn't crash or gets damaged, nor your part or the stock material or your machine. So you can't just go 80 inches per minute here. That's way too fast for going down on the Z. So we're gonna leave it at 3 inches per minute here for now, just to be safe. And we're gonna go to the geometry tab. The geometry tab for this part here, in this case, we have the selection of that we want to cut. I selected the top contour, and that's basically what we're gonna be cutting. Then we go switch to the heights tab. Where is it gonna stop cutting in this 3D contour? I selected the face. This means that the machine or the tool is gonna stop cutting when it gets to this height right here, the top height of our part, the minimum top height of our part. This is the selection here. So it's gonna do the ramp and it's gonna stop on this height right here. Now we go to passes. We don't want to leave any stock. If you wanted to leave it a little bit of stock, let's say 10 thousandths of an inch for a nice finishing, we would select stock to leave, and it would leave some extra stock right here. In our case, we don't really want to leave any stock right here, okay? So we're just gonna leave it on unchecked. And then you can also select here the maximum roofing step down here. This basically means the depth of cut, how much it's gonna cut at a time, so it doesn't go too hard on the tool or the stock material. It's 40 thousandths of an inch, 0.04 of an inch. We're gonna leave it as is. And linking, you don't really want to mess with this unless you want to have the tool starting in a specific point for some reason that, like, let's say it may crash in that place. But this is how you would have changed here. Or if you want to change the type of ramp that you want to do, if it's either a helix or just plunge it down or pre-drill, you can also change it right here. I'm gonna leave it as is, the way I had it before. I'm gonna click on cancel, but if you're programming, click on OK. All right, let's click on OK here. It's gonna calculate it again. So it's calculating the tool path, 2.9% as of now, 57%, and now we have the tool path calculated, or it's still calculating it, okay? It depends on your processor. Once we have the tool path calculated, the blue lines are the tool path. This is where it's gonna go down, and the red arrow here, this is where it's gonna go up once it's done. And the blue is the tool path, the yellow is the rapid movement, okay? That's gonna be the first operation, cleaning the top of the part. Then we wanna do the pockets. Again, remember, try to use simple 2D operations whenever you can. In my case here, I could have used adaptive cleaning, 2D pocket, or face, or no, not really face, but 2D contour. One of these three here, or maybe even more. I'm using 2D contour because it's a simpler tool path. It's just gonna go around. It's literally gonna contour around, and it's not gonna cut anything in the center. So basically, whatever's in the center here, if it's smaller than the tool diameter, it would just drop down. It's just, once it's done cutting around, this rest here is gonna drop down. Same procedure. You have to select a tool. I'm selecting an 1/8 of an inch flat end mill. Instead of being number 1 tool, number 2 tool is gonna be the number 1 tool. And then fluid coolant, we don't mess with this for now. The geometries that we're cutting here are these 3 geometries here. Inside of the circle, remember, if you have a fillet, don't select the outside of the fillet here, select the inside, because if you select the outside here, this extra material here will be all gone. This is gonna be cut, so you only want to cut what is inside, not outside of the fillet, okay? Selecting the 3 contours, then go to heights. You're gonna go from the top height, your top height is gonna be your stock top, so basically it's gonna start cutting from the stock top. And the bottom height, this is very important. I left it here set up as a stock bottom. Again, if you just pass the mouse, it's gonna show you exactly what each one means. So this is very helpful. It's gonna explain to you what it what each one means. I left a negative offset here because sometimes when you machine things and you cut it all the way through, once you're done with your part, it doesn't really cut all the way through sometimes. It just leaves like a very thin layer there. To get rid of this thin layer, I'm just giving it an offset. So instead of being 0 right here, right on the bottom of the part, I'm leaving 30 thousandths of an inch extra. So it's gonna go deeper, 30 thousandths of an inch, to make sure we cut everything on the bottom there. Once you have this done, you have the passes. So in the passes tab, you can set up the multiple depths here. So instead of cutting, like just plunging all the way down and then cut everything all at once, it's gonna be a little too hard on an 1/8 of an inch tool. Just give it some multiple depths. That means it's gonna cut whatever you select here at a time. In my case, I'm selecting 40 thousandths of an inch at a time, so 40.04 of an inch at a time. It depends on the tool diameter. We're going to talk about it later, but depth of cut, radial and axial depth of cut, that's another topic for later. Basically, you set it up here in multiple depths, how much it's gonna cut every time. Linking again, don't mess with it unless you want it to be drilled or start somewhere specifically for some reason. Click on OK, and then it's gonna calculate the toolpath, and there you go, you have the toolpath ready to go there. It's simpler than the 3D. You can see how complex this one, how different this one is from this. So try to stick with the 2D whenever you can. Now, one last step here. I'm not really concerned about the fillets right now. This is just a short demo video. I'm gonna do fillets later. But how do we cut the outside of this part? Basically, it's another contour operation. Now, this time, instead of using an 1/8 of an inch tool number 1, I'm using tool number 2, a 1/4 of an inch, because we have more space, we have extra material to cut around. Feeds and speeds are left the same. Now, one extra feature here are the tabs. So whenever you're making something that you don't want it to drop once you're done cutting, you can use tabs. How do you get rid of the tabs once you're done? You can use, for example, a bandsaw. Take your part to the bandsaw and cut off the tabs, and then you can take it to a sander, clean up the rest of the tabs, the remainder of the tabs, so you have a clean part in the end. The tabs are very useful for fast production, high production. Let's say you want to make 20 of these parts at once, and you don't want it to be stopping the machine all the time. Just cut it all, leave some tabs, and then you can knock it out, like everything together. After you're done with the production, just take it to the bandsaw, cut it all at once. I'm leaving here a few tabs, the transparent thing here. These are the tabs. You can choose between by distance or at points, for example. If I click here, it's going to leave a tab here, tab here, tab here, tab here. I'm just using a certain tab distance, 1 inch apart from each other, so that's what I'm using. And also you can choose the tab width and the tab height. Okay, once you're done with this, go to the heights. Then again, I'm going deeper on the stock bottom, just make sure we cut all the way through the stock. We don't want to leave anything layer there. And here the passes, again, 40 thousandths of an inch. Linking, leave it as is for now. Click on OK, and then you have the tab contour generated. Now, how do we go from this to a G-code? We have programmed it all. Very first thing you need to remember, whenever you select one operation, if you click on Actions and Simulate or Post-Process, it will export only this specific task. If you select all of them or 2 of them, it will export these 2. If you select all 3, it will export all 3. But if you want to export all of them, it's much easier to just select your setup, this setup right here, click on Actions, and either generate or simulate or post-process. Generate, it's going to generate the toolpath again. It's all generated, so we don't need to do it. Now, before we post-process it, we certainly want to simulate it to see how it looks before we actually generate the G-code, okay? Now, if you want to show the stock, it's green here. If you undo the stock selection, it's not showing anymore. If you click on the stock selection, it's showing again. I'm gonna leave it showing, and I'm gonna start the simulation right here, and it's gonna show us exactly what it's gonna do. A few things here, information, it shows you the real-time XYZ position, 40 thousandths of an inch. You can actually see that it's consistent to what we programmed. Feed rate, movement type, spindle speed, everything as we have programmed. Statistics, how long it's gonna take to do this entire part. Remember, this machining time is for all 3 operations because we exported all 3 at once. So about 31 and a half minutes to do all of the operations. You can speed up your simulation here. You can slow it down here as well. And here, if you notice this time frame here, this is always going to show you if you have any problem. For example, let's say you had a red flag here instead of this yellow flag, a red flag. It's going to show you that the machine is going to crash at this time, and this is what's happening. So always keep an eye on this time frame here. It's always going to give you very good information about your part. Okay. Once you're done simulating, you see everything is okay, nothing's crashing, nothing is going all the way down and crashing to the device or anything like that. You can click on Actions, Post-Process. In this case, we're going to be generating our G-code. Select the machine that you're actually using. In my case, I'm using a Haas Mini Mill. Give your program a number. I'm going to call it like 010101 or just 0101. Post-process, select any random folder, save it, and there you have your G code right here. So as I told you, as I mentioned, the name of the operation appears in parentheses. That's a comment in a G code. So that's basically your G code from your programming. So in this video, we show you basically how to start import your part in Autodesk Fusion, switch from design to manufacture, create a setup, create your operations, and export a G code. All of these are the very basic steps for CAM, for computer associated manufacturing, for in case of CNC machining or CNC milling. Hope this video is helpful. If you have any questions, leave it in the comments. Subscribe, and thank you for watching.